This is the circuits unit, video 2. So let's review a little bit here. If we were to think in terms of water, current would be how fast the water moves. So that's kind of like how quickly the charges are moving past that point in the wire per second. Resistance would be anything that restricts the flow of water. So in terms of electrical things, that'd be things known as resistors or thin wires or really long wires, things like that. Now, electric potential, when we first talked about electric potential in the previous unit, it was the electric potential energy per unit charge. So for water, this would be how much energy each kilogram of water has. The way that that water would get its energy is by elevation. So for electrical things, then, electric potential then, or the voltage, would be how much energy each coulomb of charge has. All right, now let's go ahead and start talking about some of the mathematical models. First thing we're going to do is we're going to talk about Ohm's Law and electrical power. So Ohm's Law gives us a way for calculating resistances of a material when it's attached to some sort of potential difference or some sort of battery. So our battery would be our V, and then we have a current, I, flowing through the wire, and then we're going to have some sort of resistor, R. Ohm's Law tells us that the voltage of the battery, which we call EMF, equals IR. So this is V or EMF, if you will. Now, using conservation of electrical charge, since current is charge over time, that means that we can think of current in the same manner that we think about charge. So if I have 10 coulombs of charge leaving the battery, I have to have 10 coulombs of charge returning to the battery. That way I have conservation of charge within the system where the circuit is the system. So if I have the same amount of coulombs returning to the battery, it should make sense that I have the same amount of current. So if I have 12 amps of current leaving the battery, I had better have 12 amps of current returning to the battery. So conservation of current would be the same thing as conservation of electrical charge. Resistance is measured with a unit called the ohm, named after Gregor Ohm. He was a German scientist. And again, resistors convert electrical energy into thermal energy. So we measure that with power. Remember that power is the amount of work done per time, or the amount of energy per time. For example, a 2-watt resistor converts 2 joules of electrical energy into 2 joules of thermal energy every second. So after 1 second, we've converted 2 joules. After 2 seconds, we've converted 4 joules. After 3 seconds, we've converted 6 joules, so on and so forth. So looking at electrical power, we can do a little bit of math with this. So electrical power, or power, is the derivative of work with respect to time. Don't forget that work is the integral of the force vector dotted with a displacement vector. So since we're talking about electrical things here, the force would be KQQ over R squared, where we're going from some initial position to some final position. And our dx becomes dr. Everything's nice and parallel, so the dot goes away. what we get then is that work equals then K, uh, K, Q, Q over change in R. Remember that the change in electric potential equals the work per unit charge. Well, the work was KQ, Q over R. So if I were to plug this in here, notice that the little q's are going to cancel out, and we get our electric potential to be KQ over delta R. Well, if that's voltage, what we can do is we can do a quick little, just kind of thinking about this. Notice then that work would equal delta V times Q. And actually, I guess we can just take this formula here and kind of just do a little bit of algebra and solve it for work. So we see that work is voltage times charge. And that should make sense because voltage is how much energy each charge has. So energy will be the voltage multiplied by the charge. All right, let's go back up to power then. So power is the derivative of work with respect to time. So I can now plug in my equation for work. So I have D, and then I got this V times Q, voltage times charge, all that times dt. And I can distribute that D over to the V. So I have my voltage dQ over dt. Now notice dQ over dt, that's current. So I see that power equals electrical voltage times electrical current. So the volt times the amp equals the watt. Resistors with higher power ratings tend to be physically larger. If you exceed the power rating of a resistor, it will melt or catch on fire. Kind of fun. Okay, so if we were to apply Ohm's law, which is we can think of as V equals IR, or EMF equals IR, and the power equation, P equals IV, I like to write it like that instead of VI. If I take these two equations and start to do some math with them, I can see that I have a bunch of different combinations using algebra. That leads us to the electrician's wheel. So this right here is the electrician's wheel, and basically it's using those two equations to solve for different things. So notice that I get my V equals IR right there. But V also equals power divided by current. V also equals the square root of power times resistance. Basically, we're just putting these two equations together in different ways. And I'll let you figure out how those were put together to get those different equations. But hopefully you can see it's just simply the power equation in Ohm's law in multiple different ways. Now we need to talk about ohmic versus non-ohmic resistance. You see, the resistivity typically depends on the temperature of the material. If I were to have an ohmic resistor, that means that the resistance is consistent for a wide range of voltages and currents. So a wire is ohmic. A little carbon filmed resistor is ohmic. And if I were to make a voltage versus current graph, I would get the straight line right here. So V equals I times R. I can kind of rewrite this to say that V equals R times I. And notice that looks a lot like Y equals MX. So here I see that the slope of this line would equal the resistance of the material. A non-ohmic resistor does not obey Ohm's law. So the resistance is not consistent, and it changes. Usually this is the graph that it looks like. It's no longer linear. One example is diodes, but another example light bulbs. Light bulbs get hot, so they never really obey Ohm's law. So we have to be careful with Ohm's law. It doesn't always work the way you think it should work. Okay, this is going to conclude video 2. And video 3, we're going to start really diving into the theory of circuits.